Here we go. Once again, we're going to record this because I don't have a 1.2 lesson recorded at this point. So what I'd like you to do is begin here. Oh, and you'll notice with my notes, similar to what you probably saw in grade 11, once again, this is something that I started and other people have adopted, putting in kind of the measures of success. So let's see, by the end of this lesson, I will be able to use the remainder theorem to determine the remainder of a polynomial without actually dividing. So this question that we just did here, we did this synthetic division to figure out, oh, my remainder is -6. Today what we're going to do is we're going to learn a way to find the remainder when dividing two polynomials that doesn't require any kind of division. So we'll find a shortcut to find just the remainder. Then I can use the factor theorem. So we'll learn another theorem. A theorem is just something that can be proved. We're not going to go over, well, we will go over one of these proofs. I'll go over the factor theorem proof and show that it always has to be true. And so the factor theorem is going to help us figure out how to factor polynomials. We already know how to factor quadratics. You did a lot of that in grade 10 and grade 11. Now we're going to look at factoring degree 3, degree 4, degree 5 polynomials. So up to degree 5 is what we need to do for this course. And then we'll factor a polynomial algebraically, and we'll also come to an understanding of how can we actually factor it by looking at the graph, because that'll help us too. All right. So I would like you to do these 3 questions. So the first one, you're just doing probably long division. And second one, synthetic or long division, your choice. And then the third one, just think of function notation. If p of x equals this polynomial, p of -2 just means we do what? Dustin says, yep, replace the x's with -2 and evaluate, figure out what that gives you. Okay, so I'll give you a few minutes to do that. My answer for number 1 is up. For number 2, just make sure you have those placeholders in for the missing terms, including the missing constant. A lot of you remember that. That's great. There's my answer for number 2. Anybody have a question? So I've got a remainder of 30 in the quotient, 3x squared minus 6x minus 15. All right. Number 3. When I replace the x's with -2, p of -2 is equal to 30. Oh, interesting. 30 shows up in question 2 as what? As the remainder. Yeah, that will always happen. Which is why as I mentioned, I prefer using this method for synthetic division, where I look at this x plus 2 and say what value for x makes that 0? -2. So then we use that -2 here. That -2 is what I can plug in my polynomial in place of the x's, and if I do that, the result that I get is the remainder. Happens every single time. So, oh, maybe this is the one we're going to prove. Here's what the remainder theorem says. When some polynomial p of x is divided by a binomial x minus a, where a is an integer. So we're just going to stick with integers. This would also be true if a was a rational number. Does it work with irrational? I think it works with irrational as well. For any real number, it would work. For our purposes, we're going to stick with integers. Okay, integers, whole numbers like 0, 1, 2, 3, 4, 5, and their negatives. So the remainder will always be the value of p of a. So again, the way this is written, we have this x minus a as our divisor. So what value for x makes that 0? Oh, when x is equal to a, and so a is what we're plugging in place of x in the polynomial. Now, just a side note that I put underneath here. Up here, I said a is an element of the set of integers. So that's what that notation means. Math has its own code of symbols that could get really complex. We don't get very far into it. But this is not an E, it's actually a symbol that means is an element of in math. You've used it before as you've used set builder notation. Alberta Ed uses the letter I to represent integers, so that's what I will do in the course. Generally in math, beyond high school, the letter Z is actually used to represent integers. So in your workbook, Z will be used to represent integers because that's what the publishers chose. So you just need to recognize in your textbook, Z represents integers. For Alberta Ed, I will represent integers. So that's what we're referring to. All right. Here we'll prove this theorem. Proving a theorem requires, if we look under reasoning, this poster at the side, and reasoning talks about inductive and deductive reasoning. A proof, there are inductive proofs, but the proofs that we're going to look at in this course will be deductive reasoning, where we start with a statement that we know is true, and then we apply rules that we also know that are true, legal steps in math, to show that we get a result that we're looking for. So in this case, as we look at what we have written here, this is the division statement that we've been using, well, that we used yesterday, where you say some polynomial could be equal to its divisor times a quotient plus some remainder. Always true. So that's where we start. The remainder theorem says P of A should give me the remainder. So since here I have an x minus a, I'm going to say, well, let's replace all the x's with a's and then see what happens. So replace the x with an a, replace the x with an a. Here we already had the minus a in the brackets. This x replaced with an a. A proof always, because it needs to be general, works with variables instead of numbers. If we were to do this with numbers, we'd say, well, that could verify to make us more confident that this statement is true, but it doesn't prove that it's always true. So if we can do it with variables, that shows that this is always going to be true. So that's why we're using variables here. So on the left, I'm just going to have this P of A continuing down. But on the right, if I do A minus A, what do I get? 0. Doesn't matter what A is, it's always going to be 0 when I subtract A minus A. And what's 0 times anything? 0. So notice we're applying these properties of math. Something subtract itself is 0. 0 times anything is 0. Which means, oh, and I guess we could say 0 plus something is just the something. So P of A will always give us the remainder. So there's a proof that this theorem is always true. So let's use it. For 4 and 5, we're going to use the same polynomial, the 2x to the 4th polynomial, and we just want to find the remainder. So the remainder theorem says I can replace the x with a number, and to begin with here, since I have x minus 3, the number I want to replace all the x's with is a positive 3. So if I plug a positive 3 into that polynomial and then just evaluate, that will tell me what my remainder is equal to. Oh, I wish I set up my document camera, but I haven't. So I'll have to explain some steps here that are a bit of a shortcut. So because we're going to use this polynomial a couple of times, I'm going to show you, kind of guide you through how you can use your calculator to be a little more efficient. So particularly if you have a TI-84 plus, that's what most of us have, so that's what I'll go through. For other calculators, if you can copy and paste a line, then that will work as well. What I'm going to do is I'm going to enter this polynomial exactly as it is with the x's in it. Okay, so just in the home screen, I'm not going to y equals. Just in the regular place that you do your calculations, I'm going to enter this expression with the variables. Okay, do you have that entered? So once you have it typed in, just hit enter once, and it's going to give you some number. My calculator is giving me a 3. What's your calculator giving you? A 3? Lots of people, it's giving you a 3. So I'm guessing that your calculators, you probably haven't used it a whole lot since it was reset from some test or something. So now what I want you to do is just type x and enter. And what did you get? 0. So what your calculator did is it plugged in 0 in place of all these x's, and it told you the value when x is 0 is equal to 3, because the 0 is what your calculator is set to have stored in place of x as a default when your calculator is reset. I don't want a 0 in place of x. I want a 3. So I'm going to put 3 store x and enter. So now my calculator has 3 stored in place of x. I already typed out this whole polynomial. I could retype the whole thing, but I don't have to. What I can do is I can hit second enter once, and then hit second enter again, second enter, and keep doing second enter, and it goes back to the previous line. So you hit second enter until we reach this polynomial again. Once you see the polynomial, hit enter once. And now it's giving me 0. Is it giving you 0? Anybody? I'll give you a minute to check with your neighbors, but what that's telling me is that if I replace all the x's with 3, I get 0. So take a minute, make sure your neighbor is getting this to work.
Negative 4.6 when I did x.
So, so this is what's stored in place of x right now. So what we'll do is, yours worked out? Okay, so what we'll do is we'll say 3 store x. Oops, we're going to clear that first. Okay, 3 store x and enter. So now that's stored. So now we'll do second enter until we get back to the polynomial. Second enter. There's the polynomial. Now hit enter. There you go. Are we all good? Okay, so you just do the 3 and then STO and then X. Yeah. Now that you know how to do that, use your calculator to do number 5. There we go. I'm practicing my mental math here. Hopefully it's going to work. So I think that's what I should be getting. And then if I do 40 minus 20 is 20, minus 10 is 10, plus 32 is 42, plus 3, 45. Did you get 45? Woohoo! My brain still works. Any questions with this? Nope, we're good. All right. Now here's a question that's a little bit different, where we can make use of the remainder theorem. So we have this polynomial with a missing coefficient. But we do know that if we divide by x minus 1, we know we get a remainder of 2. So using the remainder theorem, it tells me that p of something is going to equal 2. P of what equals 2? Just call it out. P of 1. Yes. So again, we're looking to see what value for x makes that 0. Oh, if we come back to this proof, we said, what's the value of x that makes this divisor 0? That's what we were doing here. We were forcing this divisor to become 0 so that when it's 0, our result is just the remainder. Okay, so we had kind of forced this proof to happen. So if I know that's true, then I can just substitute the 1 into my polynomial. Kx squared plus 7x minus 8 should equal 2. And replace all the x's with 1. And then I have an equation with 1 unknown, and I can solve. And we get our k must equal 3. Not too difficult. But we could make it more difficult. And in your workbook, question number 14 in today's assignment will be degree 3 or 4 polynomial, I can't remember, but it'll have 2 unknown coefficients. And then it'll tell you maybe 2 remainders. And so you end up doing it twice. You get a system of linear equations like you learned in grade 10, and you solve the linear system by elimination or substitution. So make sure you try number 14. But first, let's continue on. And, well, let's skip number 7. I'll just tell you the answer. Number 7. Dun, da, da, da. If we did the division, we'd get a remainder of 0. So 23 times 123. Number 8, I would like you to do. And then number 9 and 10 also. There's my answer for number 8. I got a remainder of 0, and hopefully you did as well. Question number 9, what's the term that we use to describe, for example, this 23 and 123? How do they relate to the 2,829? We say they are something of 2,829. What? Factors. Yes, they are factors. So the divisor is a factor of the dividend. So in number 10, what we're doing is essentially the remainder theorem, where since I'm dividing by x plus 3, if I replace all the x's with a negative 3, I should end up with 0, which is what we get. Which means we found a factor, which sets us up for the factor theorem, which is just a small extension from the remainder theorem. When a is an integer, x minus a is a factor of the polynomial p of x if, weird, if p of a is equal to 0, which means the remainder is 0. This is the key to being able to factor polynomials of higher degree, like higher than degree 2. On the next page, we'll start factoring. Here, we just want to find out, is each of these binomials a factor of that polynomial? So this, again, is where that calculator strategy comes in handy, because we're going to reuse this polynomial multiple times. And so we want to plug in, to begin with here, I'll replace all the x's with what number? A 1. Yep. And this is going to tell me what the remainder is. So that'll be 1 plus 2 minus 13 plus 10. 1 plus 2, 3, minus 13, negative 10, plus 10, 0. Which tells me, I have it over there, yep, that x minus 1 is a factor of the polynomial we're looking at. I'd like you to check the next three. I'm going to start pulling out my answers here. X minus 2 is a factor. X minus 3. I didn't actually evaluate. I just looked at it and said, wait, that's not going to equal 0. And sometimes you can do that. So as we look at number 13 here, I said, well, I have a negative 12, and then plus 18 is already going to be positive. Plus more is positive. Plus more is positive. It's never going to get to 0. So I actually didn't do the evaluation. I just recognized, oh, this can't be 0. And as long as I know it's not 0, that tells me it's not a factor. So if I was asked what's the remainder, I would have had to actually calculate it. But this question is just saying, is it a factor, yes or no? It's not, I could tell. Then for number 14, this one does turn out to be a factor. It is equal to 0. I didn't show that it works out, but it does. Questions? Nope, easy enough. Now, in questions 11 to 14, the constant terms. So what I'm asking here is, how does this 5, let's see. How are the constant terms of the factors? Okay, so we don't want that 3. Whoops. Undo. Erase. There we go. So I don't want the 3. I want the 5. And I want the negative 2 and the negative 1. How are they all connected to that 10? And you would tell me they're all factors of the 10. That has to be true. So if I know that's true, that means if my constant term is a 10 and I'm considering x plus 3, is 3 a factor of 10? Nope. So this will never end up being a factor of that polynomial, because this constant is not a factor of that constant. But just because this negative 2 is a factor of 10 doesn't guarantee that x minus 2 will be a factor. For example, if I looked at x plus 2, well, this 2 is a factor of that 10, but x plus 2 is not a factor of that polynomial. You could go through the steps to check. But this polynomial is degree 3. If you think of quadratics, which are degree 2, how many factors can they have? 2 factors. Degree 3 polynomial can have up to 3 factors. We already found the 3 factors, the x minus 1, the x minus 2, the x plus 5. Those are the only 3 factors of this polynomial. So the factor property tells us if a is an integer, suppose a is an integer, if x minus a is a factor, then this a will be a factor of the constant term in the polynomial, which is what we just observed. So in our binomial, this term has to be a factor of the constant term in the polynomial. If our factors are going to have integer values, which for this course they will. All right, now we're ready to go through all the steps of factoring. What I'd like you to do is close up your notes. We're going to practice some focus on what's happening, and then I'm going to hide my work, and then you're going to pull out of your brain some retrieval practice, the details of the question. Okay, so you should not be writing anything down as I go through the question, and then I'll give you some time to fill in this question. All right. So I have some steps in the process. So I'll show you later. I'll show them again. So here are the steps I'm going to go through. I'm going to start by finding the factors of this constant term, because that's going to help me decide, well, which binomials do I need to check as possible factors? There are many that I don't even have to look at. For example, if I talk about, could this be a factor of that polynomial? Nope, can't be, because -5 is not a factor of -14. So I'm not even going to consider this polynomial. So what I'll do is I'll make a list here of possibilities. So I'll think about the factors of -14. Well, 1 goes into -14. It could be positive or -1. I don't know. So I'll always consider positives and negatives. Positive or -2 could go into 14. Positive or -7. Positive or -14. So that gives me 8 possible factors that I'm going to start doing some guessing and checking to see which will be a factor. So that's step 1. Step 2, I'm going to start substituting these into the polynomial to see when am I going to get the polynomial equal to 0, which means I have a remainder of 0, which tells me I found a factor. So I'll start pulling out some previous work here. So p of 1 not equal to 0. I didn't show the details. I'm okay with you not showing me all the details because your calculator can do that efficiently for you. So I don't want you wasting time writing everything down if you don't need to. If you want to, go ahead, but you don't have to. You do need to at least show me that when you've found, oh, p of something equals 0, at least write this much down. This much tells me that x plus 1 is a factor. Factor. There we go. Good. Because p of -1 equals 0, that's going to be the value for x in this binomial. What you could think of is here we found when x equals -1, if I rearrange this, I get x plus 1 equals 0. Oh, that x plus 1 is my factor. Okay. Typically, we'll get to a place where we just do it all in our head. All right. So we have figured out our factor. Step 2 is done. Step 3, we're going to divide this factor into that polynomial and see what we get as a quotient. We can use synthetic or long division. I'm going to use synthetic division. So again, I'll look at my coefficients. So this is going to be step 3. And I'll have 1, 6, -9, -14. And I'm using this -1 to show that I'm going to divide this by x plus 1. So go through the process, bring down the 1, multiply -1. Add 5. Multiply the -1 and 5 is -5. Add those, and I get -14. -1 times -14 positive 14, add them up, and I get 0. This is a key point in our process. This is telling me I get a remainder of 0. Excellent, because this already told me I should get a remainder of 0. If I'm not getting the remainder of 0 down here, I know I've made a mistake. So it's a handy checkpoint. Up to there, we good? All right, so step 3. We have found that so far our polynomial, did I call it p of x? I did. I'll just rewrite the whole thing. There we go. Try that again. X cubed plus 6, x squared minus 9, x minus 14 is equal to my divisor, x plus 1, times my quotient, x squared plus 5x minus 14. At this point, if my quotient was degree 3 or 4, because we're expected to be able to do this up to a degree 5 polynomial, then I would have to repeat. So I would go back to my list up here and try another one of those. It could even be the same one, because we could have a repeated factor. So I could try the negative 1 again, because maybe there's going to be a second negative or x plus 1 factor. I don't know. I know that I don't need to test the 1. If it didn't work in the original polynomial, it's not going to work in the quotient either. Okay? At this point, though, we have a quadratic. You know how to factor quadratics. So we can just go to factoring from here. So I'm running out of space, but my final answer, we'll look at this and say, what multiplies to negative 14, adds to 5, 7, and negative 2? X plus 7, x minus 2. And there we have our factored form for our original polynomial. So this was step 5 here, factoring the quadratic. What was step 4? Oh, repeat. We didn't have to repeat because we just had a quadratic at this point. Good? Now I hide it. What can you remember to write down there? The list of steps I'll give you later. So don't worry about writing the list of steps. Just show the steps for now. Show the process. Oh, by the way, it's most beneficial if you don't talk to anybody else first. See what you can pull out. Then as you need to ask other people. Yes.
There's multiple factors. We only use one to get something out of quadratic.
To come. Here you can see my answer for number 17, the process. You may need to pause the video to get through the details because I'm going to just skip through it fairly quickly. Make sure you rearrange the terms so we have descending powers of x when we do the synthetic division. But I wanted to point out here the factors and how they connect to the zeros of the polynomial. I'm going to leave it for you to decipher, and that's where this video will end. Thank you.